Okay, welcome to another simple engineering snippet. In this video, we will be determining the coefficient of static friction for this ball on this ramp. I hope you find it useful. Okay, a ball of mass M is stationary on the ramp as shown. It is being held in place by a rope attached to the top of the ball and, of course, friction between the ball and the ramp. The ramp makes an angle theta from the horizontal. And our goal again is to determine an expression for the minimum coefficient of static friction to hold this ball static in the static equilibrium as shown. Okay, well, let's do a quick review of equilibrium conditions. There are two. One, that the sum of all the external forces must be equal to zero, and the sum of all the external moments must also be equal to zero. Again, this ball is stationary and not rotating, so both of these equilibrium conditions are satisfied. Also, let's do a quick review of Coulomb friction. The frictional force, denoted as F sub F, can be calculated with the equation that is equal to the static coefficient of friction times the normal force. And these terms, I think, will become a little bit more clear what I mean as we walk through the example. Okay, first thing we want to do is select a coordinate system. You can define it any way you want. I prefer to have the x-axis in line with the ramp as shown. And next thing we want to do is identify the external forces acting on the ball. It's on the ball, not on the ramp. Let's be clear about that. Okay, so one acting in the positive x direction is the force due to the rope. Let's call that F sub t. And there is going to be a frictional force between the ball and the ramp, so it's good, actually important, to identify the correct direction on that. So the force of the ball is acting on the top and pulling on the top, and so it's going to tend to want to rotate the ball clockwise as shown. And so the ball will be pushing on the ramp in the minus x direction. But we're not worried about what the ball is doing to the ramp. We're worried about what the ramp is doing to the ball. So there's going to be an equal and opposite friction force applied to the ball from the ramp in the positive x direction as shown. That's the force that we need to consider. Okay, before we move on, we're going to clean this up a bit, but I want to make it clear that both the frictional force and the force due to the rope are at 90 degrees with the y-axis. And that's just going to make our, when we take our moments, that much cleaner. Okay, so let's clean this up a bit and select our ball as the free body diagram with our two identified forces shown and the direction of gravity and our coordinate system. And now let's go ahead and add the weight force and the normal force. The normal force is always perpendicular to the surface, contact surface, so it's going to be acting the way we defined our coordinate system in the positive y direction. And of course, the weight is going to be acting in line with gravity. Also, let's go ahead and identify the center of the ball as point C. All right, so now let's go ahead and apply our equilibrium conditions. And the first thing we're going to do is sum all the external forces. As typical, we're going to do it separately in the x direction, then in the y direction. So let's start off in the x direction. Clearly, there's a force Ft in the positive x direction, a force Ff in the positive f direction. But the weight force, there's a component of that in the minus x direction. So we need to determine an equation for that. And how do we do that? Well, clearly it's going to depend upon the angle between the weight and the y direction. And we need to relate that to the angle theta of the ramp. And how do I do that? There's many ways to do it. I'm simple-minded. I say that, well, if theta goes to 0, then the weight force and the normal force become in line. The angle goes to 0 as well. So, yeah, the angle between the weight and the y-axis is theta. And when we do that, the component of the weight force in the minus x direction is minus w sine theta. All right, so we're going to save that equation and also note the equation we had previously for the Coulomb force. We'll box those up and save them for use later. Now let's work in the y direction. As we stated earlier, there's a force Fn in the positive y direction, and the component of the weight is going to be in the minus y direction. It's going to be the weight times cosine theta. And so we can go ahead and solve for the force Fn, the normal force, and box that equation. We'll be using it a little bit later. Okay, well, we're going to need an expression to relate the rope force and the frictional force, so we don't have enough for closure at this point in time. So let's go to our second equilibrium condition, where we're going to sum all the moments and set them equal to 0. What is a moment? Well, the mathematical definition, it is a vector quantity, and it is r, the vector r cross f, where the vector r is from the point, in this case it's going to be the center, to anywhere along the line of action of the force vector. Okay, well, using a definition of cross product, the magnitude of the moment is going to be equal to the product of the magnitude of the two vectors times sine theta, the angle between those vectors. So we'll be making use of that equation as well. Okay, again, we're going to choose the point C. And why do we choose point C? Is that, well, the line of action of the weight and the normal force go through C. And so we don't have to worry about taking moments on that. We could actually choose anywhere, but it's just going to create additional complexity that's unnecessary. So always look at that. And yeah, the logical choice is to take point C as the point where we're going to apply our moments. And so doing that, and starting with the moment due to the force applied by the rope, F sub t. First thing I want to do is identify the position vector, R1, from point C to the line of action. And I choose to go to the point here because it makes a 90 degrees with the force, and so it's going to be very convenient. And so we can write down our equation for our magnitude. And now let's do the same thing for force F, the frictional force. Again, identify our position vector and go ahead and write down the definition. Now, you'll notice that for moment 1, I have a minus sign and not shown, but for moment 2, it's a positive sign. How did I determine that? Well, it's a right-hand rule of thumb, where when I take the vector, when I take the moment, I put my palm, the base of my palm at the point of where I'm taking the moment, in this point situation, point C, at the center of the ball, and then I curl my fingers in the direction of the force. If my thumb is pointing into the paper, or in this case into the screen, that's a negative sign. And if it's pointing out, it's a positive sign. So keep that in mind. Walk down the hallways for the first engineering mechanics statics class, and you'll see the students in there contorting their hands and everything to try to determine the directions when they're taking products and so forth. All right, so anyway, let's go ahead and apply these moments to our second equilibrium condition. So we're going to be equating them equal to each other. Clearly, sine 90 degrees is going to cancel out. And when we do this, we're going to get that the force on the rope is equal to the force on the friction. So this is going to be enough to give us closure. So let's review. We have a couple equations here. We have an equation from the summing the forces in the x direction and the y direction, moments about C, and we have Coulomb friction force. So let's put these together. So in the x direction, we have that equation. And we can go ahead and substitute in the expression for our normal force. And then we can take advantage of the fact that the force due to the rope is equal to the force of the friction. And so we get this equation. And we can solve for that, making note that sine theta over cosine theta is equal to tangent theta. And so we get that the static coefficient of friction is equal to 1/2 tangent theta. And keep in mind that that is a minimum. So as the box equation below already says, is that the minimum static coefficient of friction necessary to sustain this in an equilibrium condition is 1/2 times tangent theta. Okay, well, I hope you found this video useful. If so, please like and subscribe. And more importantly, have a great day.